This will be the only video that you will be needing on Euler Totient function to understand it, implement it and start using in your DSA and competitive programming contests. In this video, we will take a deep look on what is Euler Totient function. We will also learn 3 different properties of it. We will prove all 3 of them. Also, we will learn 2 different techniques, very important techniques used heavily in entire DSA ecosystem. Also, we will go through 2 different types of implementation for this Euler Totient function. So this video, we will cover everything. Okay, let's get started. So first thing, what is Euler Totient function? Well, it's actually a count of numbers between 1 to n who are co-prime to n, that we denote by phi function. Symbol is this. For example, let's say they ask you what is phi of 6. Well, what it says, it's a count, right? So I will write all the numbers 1, 2, 3, 4, 5 and 6. So it's a count ultimately. And count of what? Numbers between 1 to n, here n is 6, who are co-prime to n. Co-prime means the GCD of 6 and that particular number x is going to be 1. So GCD of 1 and 6 is 1. So 1 is a co-prime. But GCD of 2 and 6 is not 1, right? 2 is not a co-prime. Again, 3 is also not a co-prime, 4 is not a co-prime, 6 is also not a co-prime, but 5 is a co-prime. So the answer is going to be 2. So there are 2 different numbers in the range from 1 to 6 whose GCD with 6 is 1, and those numbers are 1 and 5. So there are 2 numbers. This is count. That's why V is 2. I hope this makes sense. So what is Euler Totient function? It is a count of the numbers between 1 to n inclusive which are co-prime to n. That is denoted by a phi function who has symbol something like this. I hope that definition is clear. For the better understanding, I have written phi function values for first few numbers. So let's look at 1. So 1 has phi value of 1. Why? Because 1 is co-prime with 1. Now let's look at the next number, which is 2. So there are 2 numbers, 1 and 2. Now 2 is co-prime with 1. That's why phi value of 2 is 1. Let's move forward. Now we have 3 numbers. Now 3 is co-prime with 1 and 2. That's why the value 2. After that we have 4. 1, 2, 3 and 4. Now 4 is co-prime with 1 and it's co-prime with 3. That's why the value is 2. Again, for 5 we have 1, 2, 3, 4 and 5. Now 5 is co-prime with 1, it's co-prime with 2, it's co-prime with 3, also it is co-prime with 4. That's why the value of phi of 5 is 4. Now for 6 we have already proved that the value is 2. See, 1 is co-prime with 6 and 5 is co-prime with 6. That's why value is 2. Similarly, you can show for the value of 7 as well. It's going to be 6. I hope by looking at this particular example and also the previous solution, the definition of Euler Totient function is clear. As I mentioned earlier, we are going to look at 3 different properties. So let's start from the first property that we are going to deep dive. So let's say P is a prime number. Then for all the numbers who are actually belonging in this particular range from 1 to P minus 1, let's call them Q. With all of them, GCD of P comma Q is going to be 1. So if P is a prime number, then phi of P is going to be P minus 1 always. Let's go back to our example. See, 2 is prime number. That's why phi of 2 is 1. 3 is prime number. So phi of 3 is 2. Again, 5 is prime number. So phi of 5 is 4. 7 is prime number. So phi of 7 is 6. This is very simple. I hope this makes sense, right? If P is the prime number, then all the numbers between 1 to P minus 1 are co-prime with P. This directly comes from the definition of prime number, that no number less than P will divide P. Okay, now let's look into the property 2. If P is a prime number and k is greater than or equal to 1, then there are exactly p power k divided by p numbers that are divisible by p. So let's say they are asking you to compute phi of p power k, right? Now p is a prime number. So all the multiples of p, like p, 2p, 3p, all the multiples of p, if you take GCD with any of those numbers, let's say 3p comma p power k, then it will be at least p, right? Because p will divide 3p and p will definitely divide p to the power k. So all these multiples of p cannot be part of p to the power k. There are total p power k numbers, but we need to remove p power k minus 1 numbers from those. All the remaining numbers will be co-prime with p power k. I hope this makes sense. Let me reiterate that if p is a prime number, then there are exactly p to the power k divided by p numbers that are divisible by p. Very simple and straightforward, right? So the GCD of p power k with any multiple of p will be p, right? So you need to remove these from p power k. All the other numbers that are left out will be co-prime with p power k. I hope this makes sense. So this is property 2. So let's come to the property 3. So count of number who are co-prime with a into b is just equal to the count of number who are co-prime with a and count of number who are co-prime with b independently. So we can multiply. This is very hard to look. If you are good with Chinese remainder theorem, then you will be able to figure this out. But don't worry, there are two different proofs to it. One follows from inclusion exclusion, other follows from Chinese remainder theorem. Inclusion exclusion we are going to look while we write code for phi of n. Actually, while we derive formula for phi of n, also we are going to look into inclusion exclusion. Right now we will follow the second approach, that is Chinese remainder theorem. So let's get started. Phi of a into b is count, this hash stand for count of z such that it belongs to the range 1 to a into b, and GCD of z and ab is 1. So there are two different conditions here. Z should belong into the range from 1 to ab, and the GCD of z comma ab should be 1. So let's look at the first condition first. So what it says, that z should belong to a into b, right? Okay. So let's say a is 2 and b is 3. So a into b is going to be 6. For this example, we are considering a as 2, b as 3. That's why a into b is going to be 6. So z belongs to the range 1 comma ab. So z can be 1, 2, 3, 4, 5, 6. Right? Now z mod ab can be 1, 2, 3, 4, 5 and then 0. Remember, ab is 6. Now you have clear 1-to-1 mapping. If we allow z to grow beyond ab, then you cannot have 1-to-1 mapping. Imagine having 7 here, z being 7, and you take z mod ab, then it will be 1. Then it's no longer 1-to-1 mapping, right? It's not a bijection then, because here you have a link and here you also have a link. As z is bounded by this particular range, you can have a bijection and you can have 1-to-1 mapping. So when I say z mod ab is equal to 0, then you are 100% sure that z is going to be a into b. Now z mod ab can be represented as pair x comma y, where x is z mod a and y is z mod b. This comes directly from Chinese remainder theorem. Look at this. Z is 1, right? So z mod a is going to be 1 and z mod b is going to be 1. Likewise, you compute for every single number and you get all these pairs and you have exactly 1-to-1 mapping. When I say 1, 0, you know z is 3. When I say 1, 2, you know z is 5. When I say 1, 1, you know z is 1. So if you have a bijection, 1-to-1 mapping between z mod ab and x comma y, rather than counting the numbers between this particular range, you can directly count the pair of x comma y. Remember, where x is z mod a and y is z mod b. So rather than computing the value of z directly, you can just compute x comma y. So this is the first thing that we derive from the first condition that we have. So rather than computing Z mod AB, or rather than computing the value of Z, because you have bijection here as well, rather than counting the value of Z, you can count the pair X comma Y. That's the first thing that we can understand from this entire observation. So let's move to the second observation. See, this is the second condition that we have. We are not going to count any Z value that belongs to this particular range. Rather, we need Z who is co-prime with AB. That means GCD of Z and AB should be 1. If GCD of Z comma AB is 1, then we can definitely say GCD of X comma A is 1 and GCD of Y comma B is 1. How? Remember, X is Z mod A. So we can write Z as A into Q plus X, right? Now imagine there exists a P, that is a divisor, that can divide both A and X. Then it definitely will be able to divide Z. And then GCD of Z comma AB will not be 1, rather it will be at least P. So if GCD of X comma A is not equal to 1, then GCD of Z comma AB will not be 1 as well. And similarly you can prove for B as well. That's why if GCD of Z comma AB is 1, then GCD of X comma A needs to be 1 and GCD of Y comma B needs to be 1. So from the first observation or the condition, what we got, rather than counting the value of Z, you can directly count the value of X comma Y. Right, because there is a bijection, clear bijection, and we proved from this example as well. And there is a proof from Chinese remainder theorem as well. Okay, from the second observation what we got, if GCD of Z comma AB is 1, then GCD of X comma A needs to be 1 and GCD of Y comma B needs to be 1. Now let's move forward. See, ultimately what we need to do, we need to count Z such that GCD of Z comma AB is 1. And we earlier said, rather than counting Z, we can just count the pair of X comma Y. So I can write count the pair of X and Y, which follows this condition. GCD of X comma A needs to be 1 and GCD of Y comma B needs to be 1. Why? Because GCD of Z comma AB is 1, then these two conditions must hold true. That's why rather than directly counting pair of X comma Y, what we are counting X such that GCD of X comma A is 1 and Y such that GCD of Y comma B is 1. Right? So these are the pairs that we are going to count. Let's say you have P and Q. P can take 4 values and Q can take 8 values. Then total number of different combinations of P comma Q you can have is 8 into 4, right? So here also we need to count the pair of X comma Y such that GCD of X comma A is 1 and GCD of Y comma B is 1. Remember, we need to count the number of pairs. So from this example that we saw, we can directly say it's a count of X such that GCD of X comma A is 1 into count of Y such that GCD of Y comma B is 1. Remember, this is phi of A and this is phi of B. So we started from phi of A into B and we arrived at phi of A into phi of B. So this is a very important technique actually. See, in lot of competitive programming problems, you need to compute or count something. So rather than counting directly, you find some kind of bijection or some kind of relation. Once you find that bijection, you move from problem P1 to problem P2 and then you from problem P2 to problem P3. See, in this example we found the bijection from Z to Z mod AB and we found the bijection between Z mod AB and X comma Y. Everything that we are discussing is when GCD of A comma B is 1. Don't forget that. So the technique that we are talking about, if you have a problem P1 and they are asking you to count something, then you find a bijection to problem P2, then you find bijection to problem P3, and if you can count the answer for P3, well, you know the answer for P1 as well because it is a bijection. So that's what we did here. By looking at the first condition, we found the bijection. and now we wanted to compute x comma y with given this second condition. We have this condition in problem P1, so you need to migrate this condition into problem P3, and that's what we did here. We migrated that particular condition into problem P3. What was problem P3? That we wanted to compute the pair of x comma y. Once we migrated that condition into problem P3 condition, we got the direct results. I recommend you to go through it once again. This is very important. The proof is very important as well as the technique.